welcome to the last talk here at GPN. It is about reverse engineering a 28-bit RISC CPU, which is awesome. And it's true nerd fashion, reverse engineering, fantastic. Jian is talking about, Jian did it. JN, sorry. And is going to talk about. Have fun.
So, is the microphone on? Yes. Cool. So, first, an outline. I'll talk about how it started, running code on the processor, the instruction set, my tools that I developed, and generally the project scope, future work, and then we'll hopefully have time for questions and answers. So, a while ago, I found an Android TV box with an HDMI input, which is fairly unusual. It's documented in the Video Operating Center wiki. So, so I thought, what does it take to use it as a capture card to capture HDMI video? So I started looking into this, looking at the board, identifying the chips, looking at the software that comes with it. So generally the signal flow is, you start with an HDMI input stream, it goes through an HDMI receiver, and it's converted to a parallel video bus, which is just like 8 bits for RGB each, and then H-sync and V-sync and clock and something else. And this goes to the SoC, where there's some hardware to write the video data into memory. But if you do this, you end up with raw HDMI frames, which is not very useful if you try to stream it over the network. Usually want compression for that. So I started looking some more. Generally, a good information source for this is the downstream Linux kernel. For this particular box, there is no source code because vendors don't care. But some other vendors actually did care, and they published their kernels, which are mostly based on the SDK from the chip vendor anyway. So I selected the one from Endless Mobile, whatever. And I found out the video decoder hardware in this, which usually decodes video streams, like in H.264 or something, can also encode. So that would be the answer to how you encode video data on this. The processor is mostly undocumented, like pretty much entirely undocumented, but some places in the code mention it as AmRISC or Amlogic RISC. So it's probably in-house development. This SoC is from Amlogic. It's been around for a while. There's a US patent describing the general setup, but you can't find any toolchain for this or anything. So I started looking some more. In the downstream kernel, you find driver/amlogic/mport/m8/ucode/h264/vh264mc.c. So mports is just where Amlogic decided to put the code for their own chips. M8, that's Meson 8, that's one of the chip generations, actually the chip generation that I had in this box. Ucode, that's microcode, but there are different interpretations of the word microcode. In this case, it's just firmware that runs on the video decoder. And you look into this file, nice GPLv2 header, nice free software, right? It includes some headers like H264C Linux.h with a big C array. Now what's that? Okay, probably the program, right? When you look at this, 1, 2, 3, 4, 5, 6, 7. 7 digits for each instruction. That's not what 32-bit words are supposed to look like. But you can recognize some patterns. Like you have these zeros there and the CC 0 something. So there's some regularity in it. So it's probably not encrypted or compressed. That's kind of interesting. I got really interested when I saw this, because there's no normal CPU architecture of 28-bit instructions. So I compared 2 versions of the same codec program, like the H264 decoder for the Meson 6 and Meson 8 generations. And it starts out as mostly the same. All the white stuff is the same. And then there are some minor changes. Here, up there, you see 2 instructions that are different. Here, in those lines, you see 2 more instructions, and then there's one with a difference. And at some point, it's very different. Next thing I did was to write a small disassembler, which just lists all the instructions in the program. You will notice that these C0 instructions that had a difference, they have some kind of number in them. 5E8 on the left side, 5FC on the right side. If you add this number to the current address of the instruction, you find these locations down there, 60C and 620. And the code is the same on both sides. So this confirms that this is probably some kind of jump instruction, or branch instruction, depending on the terminology you prefer. So that's very interesting. We have some kind of branch, just by looking at code. And then I started looking at the instructions before these jump targets. Before most of these jump targets, marked by the cross-reference lines, there's CC0, 0000, and all zeros. So thinking about, like, in a normal program, what's before a function entry point? It's usually the end of the previous function. So I thought, CC0 something is probably a return instruction. And all zeros, probably a NOP. Because that's just a very convenient encoding for NOP. Looking around some more, I found this header file, register.h, generated by genrex.org. It contains a lot of register definitions, so names and offsets in the so-called DOS area, probably not related to the disk operating system. I don't know what the name means, but it's the DOS area. So it contains names and offsets for a lot of registers. This is very useful, treasure trove of information. Because we can just look at the names and speculate what they mean. MSP, stack pointer, I guess. MPSR, we'll see it in more detail later. But some architectures have the current program status word or something. So there's probably program status register or processor status register. Makes sense. And then we have these registers which contain something like PC and then a suffix. Normally, you might expect one PC register for the program counter. Like, this is the next instruction we'll execute. But if you go back to literature, you'll find the 5-stage pipeline. Beware of the pipeline. Which is usually like fetch, decode, execute, memory access, and write back. The idea is whenever you execute instructions, they go through all of these stages until they're done. This lines up fairly well with these 4 PC registers. I don't know what P means, prefetch, I don't know. D for decode, E for execute, W for write back. And then we have the same stuff with a C prefix instead of the M prefix. Probably a second processor. We can ignore that. So, what if I want to run my own code? Fortunately, this is all in the downstream kernels. You allocate a DMA buffer in the kernel driver. You copy the program into the buffer. You make sure the processor is really stopped so it doesn't do weird stuff. You give it the address of your buffer, start a DMA transfer, wait until it's done, and then the program is loaded. And at some point, you also want to start the program, otherwise it doesn't do anything. That's where the PSR comes in play again. Just set the bit 0 of PSR, and it starts. So I tried to do this all from user space. It failed horribly. It locked up my system a few times. And then I just switched approaches and used the mainline Linux driver for this video decoder. Fortunately, it exists in the staging directory. And I just ripped out 80%. I removed all the video for Linux stuff, which I don't need. I'm not decoding video. Replaced it with a simple I/O control interface. It's horribly unsafe, but who cares? So I can just read and write registers and load new programs. So let's run some code. Basically, you have a program, you load the program, you run the program, and then just look at some interesting registers. In this case, PC, the program counter, SP, the stack pointer. Whenever there's a change, you just print the stuff, print the new register values. And at some point, you stop everything, and that's the first look at running a program. You'll see it's not stable. Something's happening. So, still the same program. The last NOP instruction is implicitly there in the previous slide, because the program is just filled with 0 by default. So the program counter is jumping between 2 addresses, 1 and 2. So that's the address of the branch and of the following NOP. This is a feature that's common in some of the classic RISC architectures like Spark or MIPS or Video Core 4 from Broadcom. The branch or jump instruction, when you execute it, it doesn't immediately take effect. The effect is delayed. So that's a delayed branch, or what you put in the delay is called the branch delay slot. The other thing, the stack pointer, it jumps around wildly. It basically takes up all the values from 0 to 63. We'll see why a bit later, but well, we can actually speculate now. When would the stack pointer usually change? It's when you make calls, because the call instruction has to save the return address somewhere, and then the return instruction later will use that. So if you just make calls repeatedly, the stack pointer will run away. In this case, it's limited in size somehow. So there are 64 stack slots for return addresses, some kind of hardware stack. But anyway, to have reliable outputs, we need to capture all the values. The approach here is still fairly simple. Load the program, start the program, wait for some time, and then you sample all the registers. So you read them repeatedly, collect all the values that you get into a set, and then you have a list of values for each register. So here we can see this this jump instruction that we have played around with produces all values from 0 to 63 in a stack pointer, and PSR stays at 1, which means running. The program counter in the different stages jumps between those two instructions. And then there's another instruction that I've seen in a program, and that's a normal jump or branch, unconditional branch. It doesn't change the SP. So that's pretty useful. You can look at what happens when we run programs and get a nice summary. I found this instruction, 603-0400. I executed it, and some other register changed. Register with a hex address of 304. And if you look at this instruction, it has 304 written in it. That's pretty useful. So it sets this mCPU interrupt mask to 3. And when I just plug in some more instructions that I found in the program, I can actually change the value. I can both change the value, which is read from a general purpose register, and change the target, the target register. This AV scratch 0 register is actually intended for storing values and exchanging them between the ARM CPU and this processor. So that's a good target. This LI instruction is load immediate. In this case, it loads the immediate 42 into register 2. And then use the instruction from above, call it a move to control register, to move the register 2 into AV scratch 0. That's pretty useful because we can now see GPR values. And also by playing around some more, handwriting instructions in hex, I figured out that there are 64 general purpose registers, which is unusually much. But it gets a bit tedious to just look at the results. So I started implementing an emulator. So I could just formalize my understanding of the hardware, and then some code to compare the output of the emulator to the hardware results. So that I could, for example, just write this program. The first two instructions are load immediate, 100 into register 1, 10 into register 2. And then this 240 something instruction was unknown. But it uses probably writes into register 24. Then I put that into AV scratch 0 and stop the processor. the result is 90. 100 minus 10. So that's a subtract instruction. Pretty cool. I played around some more and found more instructions. We have the usual arithmetic instructions, add, subtract, and, or, XOR, shift left, shift right in logical and arithmetic modes. Those work between 2 register inputs. And then we have the same with 1 register input and 1 immediate input. We have some load and store instructions, which access a local memory. We'll get to that later. Some unconditional and conditional branches. A special loop instruction, which is a kind of conditional branch with extra steps. And some bit manipulation. Notably, no multiplication. Well, can't have everything. So, those load and store instructions. There's a local memory. Local meaning it's with this processor. It's not closer to the ARM processor, but closer to this one. Of 1024 16-bit words. It's not byte addressable. You have all the load and store instructions load or store 16 bits at once. So when you want to save a 32-bit value, you have to split it and then reassemble it later. Loads can be sign extended or zero extended, which is useful when you deal with negative numbers. So if you store like -2, that would be FFFE. And if it's sign extended, that's FFFF, FFFE, which is the 32-bit representation of -2. So that's why you have signed loads, sign extended loads. There are 3 different addressing modes. You can either specify the address directly in the instruction, or specify a general purpose register where the address is, or you can use the special index register. We'll get to that. Right, loops, I mentioned it before. You can either just use the arithmetic instructions to manipulate your loop counter, and then use normal conditional branches. Or you can use the loop instruction, which does the same as the left side. So it subtracts 1 from the provided register, and as long as it wasn't 0 or isn't 0, it jumps back to the target label. This indexed addressing mode is also useful in loops, because whenever you use one of these index registers, they automatically increment or decrement by a configurable amount. So if you configure it to increase by 27 every time you use it, it will do that. Useful for walking through structs, I guess, arrays of structs. Right, the stack. That was fun. So the stack pointer takes values from 0 to 63. So that's 64 different positions. We also have 64 different GPRs. Wait a moment. There's no separate hardware stack. When you execute a call instruction, it saves the return address into the GPR where the stack pointer is pointing, and then decrements the stack pointer. If you do it often enough, it wraps around. If your call tree is too deep, it will corrupt your state. And also, return-oriented programming is possible if you want to torture yourself. right? But there's really a very small amount of memory. It's 2 kilobytes. Can't do much with that. So, in order to be able to write more useful programs, for example, video decoders, you can do DMA transfers. That's generally the layout of the system. You have the processor on the left. It can load and store from the local memory. It can execute instructions from the instruction memory. Then you have DMA engines between both the local memory and the instruction memory and the system memory, where Linux and U-boot and whatever lives. The DMA engines are controlled by this DOS interface, which is MMIO if you ask the ARM CPU, but accessed with special instructions if you ask the AmRISC CPU. This is also how programs are loaded. You load a program by making a DMA transfer to the instruction memory. And by the way, there's no protection or anything. You can just corrupt kernel data structures if you want to. Right. This is what I did. That's the tools as they currently exist. I can either start from text-based assembly. There's an assembler which turns this into the internal intermediate representation. And I can encode that into binary programs, or go the other way, analyze binary programs into the intermediate representation and print them as text. Then there's the hardware runner, which takes binaries and runs them on hardware, or the emulation runner, which takes the intermediate representation and it's a big match statement, executes those. There's some capture and comparison of results. You've seen that. There's also an instruction fuzzer, which will just generate new instructions and feed them both in the hardware and the emulation to see the differences. That was useful to find some instructions and some emulation bugs. The other big result is documentation. I now have an architecture manual of about 25 pages. Certainly not perfect, but it exists, both in HTML and PDF. So this is the assembler, basically, or the synthesis pathway. You start with a big text string, that's the assembly program. Then the lexer turns this into a series of tokens. For example, the add I here, add immediate, is a symbol. R0 is a general purpose register. 42 is an immediate. Then the parser combines these into an abstract syntax tree, which is just, okay, I have an instruction, it has a mnemonic, which is the symbol add I. The instruction also has operands, which are list of these. Then comes the first pass of the assembler, which just validates the instruction mnemonics. For example, add I is a valid instruction. That's okay, no error here. And it computes the length and length and addresses in the program. So I can use labels in the program, and the values of these labels are determined in the first pass. The second pass actually looks at the operands for any given mnemonic and list of kinds of operands. It decides whether this combination is okay or not. And if it's okay, it turns them into the intermediate representation. And finally, serialization to get to the binary representation, which can be fed into the hardware. Live demo. You're looking at it. I should explain. The presentation program is intentionally simple. I've called it simplest possible presentation program. It doesn't need to do much. It keeps track of a list of slides and their offsets in the presentation. And every time you switch a slide, it just prints a different one. Terminal input-output is proxied over Linux, and then we have a normal terminal emulator, which is KDE Console. I wanted to implement the terminal emulator in assembly, but then I didn't want to do that anymore. So, outlook and future work, like any respectable project. You could use this for security research. Codec programs process a lot of untrusted data. Video streams downloaded from the internet. It would be kind of interesting to write a fuzzer that takes the codec program and feeds it different valid or invalid video streams. But this needs more complete emulation. The video decoder hardware doesn't only contain this processor, but also a lot of specialized blocks to do things like DCT or something. All the kind of hardware specialization that's useful for video processing. You can do DMA attacks. Someone might want to write free and open source codec programs, because right now all the programs are provided by Amlogic, if they're provided. It would be interesting to explore the other processor cores. I mentioned there's this M core and the C core. I don't actually know what this means, but I guess it's management and codec or something. So I haven't tried running programs on the C core. I also haven't tried running programs on the other instances. So there's not just one instance of an M core and a C core, but like 4 of them, which probably has some slightly different hardware features. That's future work. And also different SoC generations. I prepared all of this on different hardware than I'm currently running. So there's some portability between the generations, but more research is needed. So that's basically it. The code is available on Codeberg. Shoutouts to Codeberg. There's a chat room on HackInt, which you can join through Matrix or IRC. It's called Vicigol. And yeah, thank you for listening.
Thank you. Awesome. Do you have any questions?
Hi, thank you for the talk. That was fascinating. From basically start to finish, or from when you started till today, how much time did you invest in this entire process?
That's always hard to estimate. Like in wall clock time or calendar time, this was 4 months or something. But I had a few pauses of a few weeks in between, so it is always hard to estimate. But that's a rough ballpark.
How does the DMA from the decoder core work? Is there a special load instruction that accesses kernel memory directly, or how does that work?
No, there's a special DMA engine. You can start transfers with by writing into some special DMA registers. It's somewhere in here. And once the transfer is finished, you can use the load and store instructions to access the data. So here we see the DMA transfer into instruction memory, but you can do the same with LMEM, that's local memory. And once the transfer is finished, you can then access the data in LMEM. But there's no special instruction to access system memory directly.
Oh, so you can't load a bitstream larger than 16 kilobytes into it because there's not enough LMEM for that?
I should mention there are two different memories, right? I have mentioned. I'm not actually sure how large the instruction memory is. I think it's either 8K instructions or 8K bytes. It's a bit larger than the local memory, but not by much. So you are limited in program size. But you can load overlays or something to switch between different functionality at runtime.
Were you successful in building your capture card?
I didn't try.
You mentioned that you were using fuzzing for discovering new instructions.
Yes.
Could you walk me through the process of how you detected, how you configured your system to detect new instructions you could have found?
Okay. Basically, the fuzzer knows a few different shapes of programs based on what I'm testing. Like there's one for jump instructions, which have to record where I'm jumping. There's one for arithmetic instructions, which have to record the results of the calculation. The fuzzer generates a program based on the shape. Like the arithmetic test bench, let's call it, loads predefined, actually randomly generated values into all of the GPRs, then runs the one randomly chosen instruction, and then writes the GPR state back into those scratch registers so it can read them from the ARM CPU.
Do you have the disassembled original firmware somewhere?
I haven't saved it, but the tools are online, you can do that. By the way, I haven't seen any official disassembly. So all of the instructions just look different than they look in-house at Amlogic, probably. But you can use the tools to disassemble programs, yeah.
Have you seen anything similar elsewhere, or have you searched for something that is similar in the in terms of, like, I don't know, the encoding of the instructions, or in general the approach of, you know, integrating such things in processors?
I haven't searched much, but generally, in some regards, it's a fairly usual RISC CPU, and then there are some unusual features like sharing the same array for both the GPRs and the stack. But I don't know, I haven't seen anything that's super close.
Are there some more questions? We still have time.
Yeah, hi. Thanks for the interesting talk. I'm not sure if I just didn't hear it or something like that, but in the notes to the talk, you wrote that it's not really 28-bit instruction set. I'm wondering, yeah, can you probably examine this a bit?
It's a quirk of terminology. These terms of 8-bit processor, 16-bit processor, whatever, they originate somewhere in the 80s or something. What was originally meant by this was the width of your data bus, which is arguably 16 here, because the local memory is 16-bit wide. Then at some point it got reinterpreted as the width of your general purpose registers, which is 32 here. But the interesting part here is the width of the instructions, which is 28. So really this is a vague term, and I used it for clickbait.
Apparently it worked. Yeah, we still have some time left. Oh yes,
one more
more
question.
questions. That's great.
Like, aren't the registers on the stack like something like a register window?
No, the registers always point at the same physical register, as far as I can tell. So when you write R13 or something in your program, it's always the same register. What shifts is only the stack pointer, and all the stack pointer does is store the return stack with return addresses. So it's not like register windows in Spark or something.
Yeah, thank you very much. I hope you had a great time.
Oh yes, certainly.
Applause again. For Jim.